Yeah, so the work I'm going to be presenting today is actually mostly not very new. So maybe a couple of people have seen this talk before, but it was the thing I found that fit most to the topic of the workshop. Just to start off, I mean, this is not all my work in isolation. I've worked with a lot of nice people on various parts of this work. You will see these names reappearing in the references at the bottom of the slides. So Oscar is currently doing a PhD at the University of Helsinki. Bert was a PhD cohort of mine who left academia some years ago. Thijs is currently a postdoc in Leuven. And Giovanni and Stefan are both still in Leuven. They're professors who were supervising my PhD. So hence, yeah, you see the slide template is the KIT template, but a lot of this work happened at Leuven, so it will quite prominently up here as well. And yeah, definitely funding acknowledgements for the Flemish Research Foundation, the DFG, and probably I've forgotten to put Eurofusion up here. Eurofusion should be on here as well. So to start with, I mean, the whole point of this kind of program is for us to have opportunity to discuss, and I'm not going to present everything I've done before. So I just wanted to give quite a brief sketch of, what do I find interesting, or at least what have I done before, so that people know what they can talk to me about other than today's work. My general thing is stochastic solvers in the sense of particle-based simulation. So Monte Carlo simulation, and I'll give an example of what that looks like in my view during the talk. But the general idea being you have, let's say, some parameter, you feed into some Monte Carlo simulation, particle-based simulation, and out comes some estimation of the solution of a PDE. Then we call this Q. And this will typically be something noisy. So we do forward simulation and we get some kind of approximation of Q with our Monte Carlo solver. So we have Q hat, which is Q plus some Monte Carlo noise. During my PhD, did a lot of work on asymptotic-preserving multilevel Monte Carlo and multilevel between brackets. So these are somehow some multiscale ideas on kinetic equations. The topic of today's talk. But currently my interests are also shifting a lot towards inverse problems, and inverse problems in two senses. So you can either look at the problem of saying, okay, I have perhaps the output of a model solution to my PDE or some function thereof, so something that I want to minimize. So this could be matching the solution of a numerical solution to some data, or it could be trying to optimize some kind of design, and you want to find the parameter input. So the shape of some component, some kind of parameters of your PDE to produce the output you want. And you can look at this as directly solving the problem in an optimization setting, and then you end up with Monte Carlo simulations, or adjoint Monte Carlo simulations, and so I've done some work around there, where the trick is you have to simulate the same trajectories forwards and backwards, and using good random number generators for that. And then also Bayesian inversion, where we've had various talks, specifically how do Markov chain Monte Carlo algorithms interact with these kinds of solvers. So if any of this rings a bell, sounds familiar to you, have a chat with me. Unfortunately today is the last day of the workshop, but I will hopefully be back at some point in the future weeks. Right, so the forward simulation problem. Most of this work was motivated by collaborations within the fusion community, where I think these days this is fairly common knowledge. You have these tokamak reactors. These are these big toruses in which you have a plasma circling through the torus. This is a cross-section of the torus, and you have this fusion reaction which hopefully one day will be able to produce enough energy where you take two hydrogen atoms, give a helium atom as output, plus a bunch of energy. This is still, some decades down the road. The number of decades has remained relatively constant, or perhaps been slightly increasing over the last 60 years or so. But people keep making progress, so I'm somewhat optimistic. The design problem that we're somehow related to is this diverter, which sits at the bottom of this torus. Looks something like this. And its main function is to act as a kind of waste material particle exhaust. So the idea is after you have this kind of ash, this kind of waste material, which does not follow electromagnetic fields, so it's no longer ionized. It's the so-called neutral particles. So they, sorry again. After recombination, these mix into things. After recombination, these things get much heavier, so they drift to the outside of the reactor. And then the magnetic field lines, so they used to follow the magnetic field lines, guide these particles down, and they hit these plates here. And you want to design this component to deal with the heat load of these things hitting the reactor. So this is the kind of waste material. The neutral particles will come in just a moment. So that's here. So this is somehow a very simplistic view on the physics around this diverter. And what do we have is, here we have the two species of particles. We have the plasma, so we have the charged particles moving from the bulk of the reactor or out and hitting these plates. So this is the kind of flow from, let's say, left to right in a current conceptual model. And we model this as the fluid dynamical set of fluid dynamics equations. So these are quite dense. The equations on the top half of the slide here. Now, don't spend too long trying to figure out exactly what's written here. The main part that's going to be interesting is actually this bottom half, and these are the so-called neutral particles. Because what happens? The plasma flows to this diverter plate. It hits a plate on, let's say, on the right-hand side that you can imagine here. It recombines, it picks up an electron at the plate and enters the domain again. These things are much lower density. So we model them with a kinetic equation, and we've seen a couple of examples of different kinetic models throughout the week. Ours looks something like this. So we have Fn being the density of our kinetic or neutral particles in a phase space. So theta being our spatial variable. This comes from the fact that typically you think in polar coordinates in these applications. And v being the velocity. And what do we see? We see transport, so the particles move with the velocity they have at a given moment in time. Here we have ionization, which in this case is kind of like an absorption effect, right? Neutral particles ionize, they split into an electron and an ion, and they vanish from this equation, and they become a mass source in these equations up here. Then we have a source, right? So we have neutral particles entering the domain from this diverter. And finally, we have interaction term or collision term, and this is the so-called BGK operator, which also a couple of people have talked about during this week. So the idea is we drive our distribution in the velocity space to some steady state distribution. For those of you familiar with kinetic theory, this can often be a Maxwellian, but I'm not writing M here because it can be something else sometimes as well. Right. I put a lot of color on the slide because I don't necessarily want you to spend too long parsing the equations, but the idea is you can see that everything is connected. So everything that has a certain color means, so if it's blue, it means it depends on this equation. If it's green, it depends on this equation. If it's orange, it depends on this equation. So you have a coupled system of equations. Even though each equation itself can be solved in a linear way, or the entire combination becomes nonlinear once you iterate over these equations. So it becomes quite expensive. This, I mentioned already, it's a fluid dynamics equation. Typically you use a standard finite volume solver, something like that. Here is where the Monte Carlo simulation comes in, because what we're typically interested in is some kind of low-dimensional quantity where we integrate over velocity space, and thus we don't want to be constructing these grids in this phase space, this theta v phase space. So the simulation paradigm looks something like this. Our parameter of interest is this L theta, so what we're actually going to do here is shape optimization on the diverter. So the idea is you want to find the optimal shape of this diverter to get a good heat load. In 1D, what is shape optimization? If you consider like a domain where the diverter is on one side, well, you just adjust the length of your domain. Right? So that's what L theta is. You plug a proposal for L theta into your iterative solver, you iterate over the finite volume of Monte Carlo code, you do, say, a few hundred iterations, and out comes some objective J, you can call this. So this is somehow saying how good your simulation is. And this is what we're interested in computing in the forward problem. So with all this, we basically get a huge state space of quantities that we want to compute, discretized. And for all particles at all times, we are simulating. We have to track basically the particle position, velocity, and the weight throughout our simulations. But then we do some kind of bidding afterwards to reconstruct the solution. So that was a lot of information just to give a kind of overview. Now I want to just zoom in on these kinetic models. So just a brief recap and to make things a bit more concrete. We start again with this kinetic equation that I showed you a couple slides ago. This is going to be our model problem from now on, going forwards. A Monte Carlo simulation with particles for something like this could take the following form. There's a number of choices you can make, but you can say, okay, I split up my dynamics into 3 different parts. I start by a positional update, so I say, okay, I have a transport term. Particles move for a given amount of time with their velocity to update the position. And maybe some of you, if you are paying attention, have noticed there's no time dependence in this equation up here, but I have a time step down here. This is somehow a quirk of Monte Carlo simulation, particle-based simulation, which might be important to understand some of the things I tell later. You can have a steady state equation at the kind of PD level, macroscopic level. And then once you zoom in at particle dynamics, there is no such thing as steady state anymore. What does steady state mean at the particle level? At a given position, you have the same number of particles going left as going right, and they cancel out. So if you zoom in at the particle level, even for steady state problems, the Monte Carlo simulation is somewhat time dependent, but then when you're actually computing these quantities that we're interested in, we're taking some kind of time average over particle trajectories. So we do a positional update. After each time step, we decide whether we change the velocity or keep the old velocity based on a collision frequency, which we can compute analytically. So this is just a coin toss with a certain probability, and then finally we have a weight which can decay as a function of time. So we just have a certain ionization rate, and we reduce the particle's weight. So once you do all this, you get this. Basically, conceptually, we don't build this in practice. It's a really big vector of states. This is not what we're interested in. Like I mentioned before, we're interested in computing some kind of grid-based quantity in space, perhaps the density of particles, perhaps a flux. And the way we do that is by basically doing a kind of tallying. So I mentioned time estimation. So we sum over all particles. We sum over all time steps of all particles, and then we multiply the weight of that particle with some kind of function, which I'm exactly going to call g. This is the estimator. The estimator says, okay, I take a particle that goes from n to xn plus 1 with a certain velocity, compute some kind of weights on a grid for me. This can be, for example, how long did I spend in each grid cell, or you can make a number of modeling choices here. Finally, we then have a weight function, which is going to depend on what we're estimating. So if we're estimating a mass source, so we're interested in the density of particles, then this takes a certain form. If we're interested in estimating a momentum source into our plasma equations, then this takes a different form. So this psi is just implementing what kind of quantity are we interested in computing. So, we've seen a lot of Monte Carlo simulations so far. There's always been some point where you have a sum over a bunch of samples, and in this case, this is the sum that we're computing. Right. So in this setting, what are the challenges? So why is this somehow relevant for a multiscale workshop or program? Well, this problem is in some way multiscale. So we're interested in some relatively long time horizons. Think order maybe a second of simulation time. This is how long these pulses for these reactors will at some point hopefully become. But particle-particle collisions happen much faster than this. So you can take order 10 to the 10 events per second or higher, depending on the regime you're in. So if you have to resolve all these things in the Monte Carlo simulation, so that means taking a time step that's small enough that you can resolve individual collisions, it becomes ridiculously expensive. So what can you do? Well, okay, you can just say, well, I have money, I have a cluster, I just use up the whole thing and I just throw a bunch of compute power at it. But this doesn't scale well, and I think everyone in the room feels uncomfortable when I say something like that, because as a mathematician you want to do something a little bit more clever. But what you can do is take advantage of this kind of multiscale idea, and in this case it takes the form of a diffusion approximation for your kinetic equation. So the idea is, if you zoom out on these models enough, you can approximate them with a diffusion model. Again, the people who are familiar with kinetic equations probably think this is obvious. Some people maybe have not seen this before. I'm not going to derive this today. Trust me. But the idea is the following. We're going to use an approach, the details that you can find in this paper here, where the idea is you take your equation, you do a bunch of clever manipulations on it. I can say that because it's not my work. And you derive another equation through what's called the MX approach. Again, the details are in the paper. For those who are familiar with kinetic theory, I have explicitly put epsilons here, those are the Knudsen number, to sort of say, so you can have a bit more intuition about this. For the others, just ignore those symbols. But the idea is, what we've done here is derived a PDE, which has a couple of weird things. Okay, there's an extra term, fine. There is also a time step here. Now, I can say for those worried about me having a discrete time step in a steady state equation, what you do is you add a time derivative here, you do some derivation, and you remove it again to get this equation. So you go from steady state to non-steady state back to steady state. That's all being pushed under the rug. But it's even more weird that you just have a time step in a continuous equation, right? But the idea here is that what we are going to do is use this delta t as our simulation time step in the Monte Carlo simulation. And I want you to just sort of mentally try to take two limits in your head, visually, by looking at this equation. So what happens if we take very small time steps? So imagine delta t goes to 0. Well, this becomes the same as what you have up here. This remains unchanged, this is unchanged. And this here also goes back to what we have up here. This term vanishes. So the two models are somehow consistent, and the consistency rate is order delta t to each other. So if you take very small time steps, you're simulating the same model. If, on the other hand, you take very large time steps, so just plug in infinity, and we don't do that in practice, but just bear with me, right? This becomes 0. This becomes 0, so you get rid of your transport and collision effects. And here you get something that's order 1. So you have infinity over infinity, and you get order 1. So this is a diffusion equation. I'm just waiting for everyone to look like they're agreeing. So the idea here is that you have a model that somehow adaptively varies with the time step. Diffusion doesn't have a time step constraint. You can take large time steps, it's going to be stable to simulate, but it's a biased approximation. The diffusion model is somehow implicitly assuming that we have an infinite collision rate. So that's one assumption that's hidden in this diffusion model. So it's a biased approximation, but we can take large time steps and get an initial rough estimate that's close to what we want to compute. If we take small time steps, we are computing the correct model, so we get accurate computations. So what does that make you think of? multi-level Monte Carlo has come up a lot throughout the talk, and that's going to be the idea.
I have a question.
Yes.
I'm a little bit confused about all the V's. There's a normal V and a V bar and a V tilde.
Yeah, so V tilde, sorry, I didn't introduce that. V tilde is our characteristic velocity, so that's the expectation of V squared. That's the characteristic velocity, so this is the expected norm of the velocity. And so in absolute terms, or in squared absolute terms, the V bar is some kind of the normalized velocity. So when you look at the AP schemes, you write everything in terms of something that's order 1 times an epsilon. So that's just V bar.
Thank you.
So before I get to the multi-level Monte Carlo, what does a Monte Carlo scheme look like here? Well, I already showed a Monte Carlo scheme for the classic case. Here we have an alternative where basically we do something very similar. We have a positional update. We have our velocity here with some weighting now that comes from this term in our PDE. And we have a diffusion increment. So we have a diffusion up here, second spatial derivative. And at the particle level, this becomes a kind of Brownian motion to simulate. So we sample normally distributed increments and we scale. And then the ionization, collision events, we do basically the same way, just with slightly varying weights. So these weights depend on delta T. So that brings me to multi-level Monte Carlo. And yeah, this is a slide you have seen before. The notation is just a little bit different. So what do we have? We say, okay, we start by taking very large time steps. We simulate lots of particles. And compared to a problem where you're simulating a PDE multiple times and each solve for PDE is a sample, that takes a different meaning here. So, I mean, a small number of particles, in my mind, is like 10,000 or 1,000. A lot can be millions or higher. This is what we do. We take our estimation that we did before. We sum over very many particles. We get an initial estimate with a bias. But it's low variance because we do many samples, and we have to estimate this bias. And we do this through a sequence of difference estimators where we correlate at the particle level. So we're not doing, I mean, again, we've seen lots of talks where people run the same simulation for the same sample, input, and do that to correlate. What we're going to do is try to make the trajectories that go through space, through the space, follow the same random walk somehow. And get correlation that way. And you do a pairwise comparison for each pair of trajectories, with one following large time steps and the other following small time steps. How do you do that? The idea is the following. On the top, we have our fine simulation. So we have, and my refinement factor is going to be capital N. Capital N small steps for the same amount of time as a single step here. If you have these two trajectories, you can correlate them in the following way. You take the fine simulation, you run it for capital N steps. Each of these steps, you generate some random numbers. So you might be sampling velocities, you're sampling these normally distributed increments for your Brownian motion, you're choosing whether or not you have a collision, and so on. You store these M sets of random numbers, and then you combine them together in some way to generate a single set of random numbers with the correct distribution that you can plug into your course simulation. And if you do this in the right way, these two things will be correlated. Now, the right way takes a bit of thought, so this was done over the course of 2 papers, which you see here. So let's say final approach we sort of converged on is the following, right? We have velocities at each of these steps, and we take some information from the velocities in the fine simulation and use this to generate a velocity, or let's say kinetic increment at the course level. And we do the same with the normally distributed increments for the Brownian motion, but we also have the initial coupling in this direction. And the idea behind this is that if you take very small time steps, the kinetic dynamics are dominant. That's what I've said a couple of times already. So in somehow the extreme case, in the fine simulation, this isn't doing so much, this is doing most of the work. Vice versa, in the coarse simulation, this is doing less work and this is doing more work. So if you want to get a good correlation, you somehow have to bring information from here to here to make the coupling good. Another intuitive sort of thought behind this is that this diffusion is somehow conceptually replacing very many of these small kinetic increments. So what you're doing is you have lots of straight line travels of particles, and the diffusion is somehow assuming, okay, if I take many of these and I sum these, I somehow through the law of large numbers get a diffusive increment. And that's why this term has a larger weight in the coarse time stepping. So again, we have to take some information here to do this. And in the next couple of slides, I'm just going to work out first the green arrows and then the orange arrow in a little bit more detail. So the green arrows, the idea is the following. We have a bunch of fine diffusive steps. Don't know how I did that. We have our fine diffusive steps. These are normally distributed increments. You can sum these and get another normally distributed increment. So you have to rescale to get the correct variance. And with the velocities, you can also just sum all the velocities that these updates and rescale them in a similar way. The formula here is a little bit more complicated, so I've just hidden it from you. And then you need the two quantities, which at least have mean 0 and variance 1. That's what we require. If these are also sampled from a Maxwellian, they might actually be perfectly normally distributed, but in other cases they might not be. But then the first two moments are still correct. And there is literature on this kind of weak Brownian motion, so you can sort of simulate Brownian motion with an approximate process that has the first couple of moments correct, and then at least will work in a number of cases. In this case, gives us reasonably good estimates. And I'll get to a correction that you can do if you don't have this, if you really want to make sure it's completely correct. But if you have mean 0 and variance 1, you can combine these two things in the following way. So you choose your theta, which is some arbitrary number between 0 and 1, or arbitrary. If you want to get good correlation, you have to pick the correct value. But it's a value between 0 and 1. And then this quantity has mean 0 and variance 1, and you use it in your coarse Brownian motion. So, yeah, if these velocities are not normally distributed, if they're not normally distributed, you can correct this, because remember we have multilevel Monte Carlo, right? We don't actually have to simulate something that's perfectly correct throughout the hierarchy, we just have to correct it and do the correcting at the finest level. What is the issue here? You have to somehow tweak so let's say you take a coarse and a fine simulation, and you generate the coarse simulation in this coupled pair in a slightly wrong way. Then the fine simulation in the next level, next level up, needs to also do the same dynamics so you have a consistent telescoping sum. So what we have to do is find some way to approximate this distribution that we get by summing over these velocities that may not be normally distributed, and sample from this to generate independent samples from the same distribution without simulating this process, because otherwise we're doing all the work we would have to do in the finer level, which defeats the purpose of multilevel Monte Carlo. And we came up with a way of doing this, at least an approximation. So what we want to do is approximate sums of this form without sampling n of these velocities. And if you sketch this, you can sort of look at it this way. So imagine we have capital F being whatever this is, 1, 2, 3, 4, 5, 6, 7, 8, 9, 11 steps. And we have a process that had a collision after one step, then on step 3, and then so on. So green is, you went 2 time steps without a collision, or before we encountered a collision, and green is we went 3 time steps before encountering a collision. And you can somehow just rewrite this sum as, instead of a sum over m steps, a sum over some unknown pi of the number of steps that you kept the velocity times the number of velocities that you sampled. So That's the first rewrite we do. Once you've done this, these v's are no longer dependent on each other, so you can reorder the sum. And that's basically what this notation means. We rewrite it in the following way. So now we say we group all the ones that are, we keep a velocity for length for 1 time step, and then we see, okay, 3 times the cube velocity for 2 time steps, and so on. And then once you do this, you actually can get away with, and this is what's written here in formulas, saying, okay, I actually need to sample 2 distributions. One, I need to figure out, okay, I need to sample the so-called run length distribution. I need to figure out, okay, how many times, if I have m steps, do I have a velocity that only stays for 1 time step? How many times does it stay for 2 time steps? How many times does it stay for 3 time steps? And we found a paper from, I think, 1994 that had an efficient algorithm for doing this in a relatively good way. It's still a little bit approximate, but works relatively nicely. So you can sample this, you can generate a table, and then sample from that table. So you have to do some pre-computation and you get that. So once you have that, you then have this prefactor here. So this lambda star is basically saying, this is the number of times that I have a velocity that lasts for x, for 1 time step, or 2 time steps, or 3 time steps. So that's what this lambda is, the number of time steps you last for. So then we want to compute this. When we want to compute this sum, we have to compute this quantity, and then we have to sample from some kind of table to say, okay, I have to sample from the distribution of the sum of 2 time steps, the sum of 3 time steps, the sum of 4 time steps, because what we do is we multiply 1 by the sum of 2 velocities. Here we multiply 2 by the sum of 3 velocities, and here we multiply 3 by the sum of 1 velocity. And we can tabulate all of this. It takes a bit of work, you can do this. And what you end up with is rewriting this as a sequence going from 1 to m, where now this sequence is somehow, you can think of it almost like a Fourier way, the length of steps, or the length of the number of the sequence of time steps without collisions. So that's what this sum is. And then you sample the contributions of these different things. And you can truncate this sequence arbitrarily because you assume that very long sequences without collisions don't happen. And we have some kind of tweaking we can do in terms of cost accuracy. So the details are in the paper. Now, let's take a step back and look at, just to make sure we're all on the same page, this orange arrow here, right? So we've done this. The orange arrow, the idea is, okay, what we want to do is say, at the end of this coarse time interval, so m fine steps or a single coarse step, we want the velocities to be aligned, to make sure the particles are correlated. The way we do that is we actually think about, okay, how do you simulate this kind of coin toss effect in practice, right? You have a chance of a collision or not a collision at every time step. What you do is you sample a random number between 0 and 1. You check if it's over the probability of no collision taking place. And if it's larger than that probability, then you decide to simulate a collision. So if you draw these u's, the larger u is, the more likely it is to produce a collision over each of these m steps. Right? The largest one is the one that is most likely to have produced a collision in the whole process. So you can just take the maximum and put that in your coarse simulation. The small tweak, you have to take the mth power because you want to make sure that you still have a uniform value when you're simulating your coarse simulation. And the maximum of m values is uniform values is not uniform, but its nth power is. This is directly applying the inverse CDF approach. And once you do that, you basically make sure you correlate the two velocities. If both simulations have a collision, you take the fine simulation and use it to generate the final velocity for the fine simulation. You plug that into the coarse simulation, and they have matching velocities at the end. And you can demonstrate, and this is also in this paper, that there's always going to be at least one collision in the fine simulation if there is one also in the coarse simulation. So you always have a velocity carryover. So I got very much into the details there. Just a recap, it all comes down to this idea: do m fine steps, take all the random numbers in these m steps, combine them into a single set of random numbers in some way, and plug that into your course simulation. And then you have coordinate trajectories. And now we can look at some numerical results. So we did somehow a first analysis, looking at relatively simple cases. So this is nowhere near yet a fusion simulation. What we do is we take a one-dimensional space. We start the particles at position 0 and we compute the mean squared displacement. So that is just how far have they gone after a certain amount of time. Right, and then we have a hierarchy we construct, and this is just following the standard multi-level Monte Carlo approach to picking the number of samples and so on. What is a bit unique here is if you look at the time step types of sequence here. So we start at level 0 with something that is roughly order 1, something large, so we basically just take very large steps. And these steps are big enough that you have very many collisions in a single time step. So we're well in this diffusive regime. Then we do a single step, large step to level 1, where we immediately go a couple orders of magnitude smaller than the mean time between collisions. The idea being this intermediate regime, it has a lot of sort of nasty stuff going on there, and you can't get good correlation there. It's a kind of 1 minute or 10-second explanation. In the paper we give more explanation for why this is the optimal strategy, but basically what you're doing is transferring from one model equation, so your deterministic model, to the kinetic dynamics, and you can almost think of this like a multi-fidelity. You have two different models and you don't want to simulate the hybrid model because it doesn't make any sense. And then we just have a geometric sequence decaying down. Now we have the time step at each level, we have the result we compute with your estimator, and the sum is in our multi-level Monte Carlo estimate, the variance of sampling at the level, the number of samples, and then the overall cost per level. And we then do some kind of back of the envelope calculation, so we can't do the equivalent single level simulation, it's too expensive. So we say, okay, in this cost metric, which is somehow counting the number of time steps we do overall, our Monte Carlo simulation takes about 10 to the 9th work. Whereas if you do a single level simulation with the cost of doing everything with this time step, but taking this number of samples to get that variance reduction, so that's just a rough approximation, you would have to do order 10 to the 12th. So you get a factor of 1,000 speed up, roughly. Now this is super cool, right? 1,000, really nice. Maybe a small criticism of how multi-level Monte Carlo algorithms are often used or analyzed, right? It is one of these cases where you use multi-level Monte Carlo to get a better rate, and then if you ask me how much speed up that I can give, I'll ask you, okay, give me a speed up you want, and I'll tell you how much work I have to do to get there, right? From a practical perspective, probably we don't need this many levels and so on, so let's look at something slightly approximating the real world, and see how it performs there. Now, I'm going to present some very preliminary results here on a fusion case, something that's approximating this 1D model problem I talked about in the beginning. They are preliminary in the sense that they don't yet work. But there are some interesting lessons that can be drawn here, so I think it's still interesting to talk about them and at least say something here. So what I've done here is plotted let's say a model solution for what I showed in the beginning. This is plasma density, so the plasma is flowing from left to right here, and it sort of bulks up a little bit at the boundary that's coming in, at the diverter plate. This is the velocity, and here is the quantity we're mainly interested in. These neutral particles. So this is the neutral particle density, where the 3 lines are just 3 different simulations. So these KRs are recombination rates of the diverter plate. What you see is basically that these neutral particle density looks like an exponential decay going into the domain. So basically, they re-enter from the right, and they very quickly ionize and vanish This is kind of dominant physics there. So first we just simulate. I'm going to simulate this orange curve, and here I'm just taking the single level simulation and just plotting that single orange curve that you saw before on the bottom. This is what we want to approximate. Now note the scale on the axis. These people in the fusion community, they like to work with really big numbers. So this is the number of particles per cubic meter. Right, so let's just do that. And that's what it looks like. So we don't even have to really plot an error here, right? This is not good. So it's much more noisy. Why? I'll show some plots in a moment to explain why. But here you somehow have this, I'm just going to sort of explain what we're doing here. We have a sequence of levels, so I've just transposed the table to fit it on the slide nicely that you had before. Level 0, we take large time steps, and here large is 10 to the minus 5, because we're working with physical parameters now. And then 10 to the minus 9 is somehow small enough that we capture our collision dynamics nicely. And it goes down. But what you see is this is small, this is really big. And the estimate I've normalized somehow to make the numbers comparable. And in fact, this is somehow the key thing of the problem. What's going on here? Our initial estimate is just bad. So let's look at the different levels. And again, look at the scale on the axis. This is what we want. This looks pretty nice. This is level 1. This is our level 0 initial approximation with the diffusion equation. It's an order of magnitude off. And then when we get to level 2 and so on, we're basically estimating 0. So this is where the noise in the simulation comes from. Now, I already hinted at this in the beginning. The next slide is not how we fix this. The next slide is what we think we want to do to fix this, or okay, the slide after that. The idea here is that, so we know what's going on, and I will try to give you at least a brief idea what the problem is here. First off, this problem here. I already hinted, right, in the toy problem, we have this nice, well-behaved thing we're simulating. We can just keep adding levels and going down and just get whatever speed up we want. And we just keep getting these epsilon, like small refinements. In these kinds of real fusion simulations, people are happy if they get just a couple digits of accuracy. Sometimes even one, or maybe. I've been at conferences where people plot 2 lines which are visibly different from each other, and they say, this looks very good, this is a good match. So that's half a digit of accuracy, I would say. So it doesn't make sense to just add all these levels. Now what we're doing here is just adding noise to compute 0. So Multilevel Monte Carlo is really nice. But I think, we've heard a lot of people talk about multi-fidelity, bifidelity. I think this is somehow, in practice, often the way to go. What you want to do is couple something that's cheap with something that's expensive, and just bridge the two, and then the extra refinement, is nice to analyze, but probably doesn't actually help you so much in many practical cases. So that's my first point. Don't waste money or time simulating more accurately than you actually need for your problem. The second thing is to do with this property here. But basically what we're doing is missing a bunch of mass in our diffusive simulation. That's what you see. You have an order of magnitude off. We're only getting like 10% of our mass in the estimates there. This has to do with estimation, and this has come somehow in this kind of particle-based simulation still a big topic with lots of open questions. I could give a whole separate talk on how you construct estimators in different cases. But I probably better start to point you to other people who know more about this than I do. But fundamentally the problem is the following. I mentioned this at some point earlier. The diffusive approximation at the particle level is basically saying we have a kinetic simulation. You can imagine this blue line going from here, doing some kind of random walk where we sample velocities and let it travel in a straight line for a while, and then sample a new velocity and changes direction. And we approximate many of these steps, somehow conceptually using like the law of large numbers, the fact that you converge to a normally distributed quantity if you sum many IID random variables. with a single normally distributed quantity. That's this diffusive model. Now, when you look at these estimators, what we do is we have the two endpoints of a straight line, and you try to say something sensible about where the particle was in the meantime. And for the kinetic simulation, it's fine, right? You have a straight line from here to here. Okay, if there are grid cells along these, this bit, this one bit of the domain, that's where the particle should score, and you get some kind of sensible output. If you have this, or a much larger timeline, no clue, right? You don't know where the particle went because the straight line between 2 points is somehow a measure zero event in the diffusive. In the diffusive, if you look at a Brownian motion. And you don't even know how long the trajectory has to be, so that's where you get a loss of mass. Now, I mentioned there are approaches to fix this, so this is a paper that came out, I was going to say recently, maybe 4 years is no longer recent, I don't know, depends on your reference point, I guess. Which is a very nice idea, which would be interesting to try here. The idea being that instead of trying to do this kind of straight line interpolation, you look at the beginning locations of every Brownian motion. You store these on a spatial grid. So imagine you have just a bunch of Dirac deltas, if you want to look at a continuous model. And you say, okay, I have a PDE description of this diffusive dynamics. So I plug these Dirac deltas as a kind of initial condition into this PDE. I run a PDE solver for the amount of time that I did this random walk. And then I get some kind of spatial solution which gives me my diffusive contributions from the Monte Carlo. It feels like something to me that would work, but it has not been verified on a more complicated case set, so I cannot show you those figures yet. Right. So now I'm wrapping up this kind of multi-level story here. I did want to show something more recent. So, and I still have a bit of time, so I'll just give a quick sketch of some work we have done here, because I don't want to end the presentation with the story that this doesn't work in practical problems, because actually we are still working through collaborations with people in the fusion community on this asymptotic preserving stuff in fusion, not multi-level yet. So the code, getting multi-level into one of these production codes is going to be a task which I hope I don't ever get involved in. It's going to be a slight variant of what I presented earlier. So I talked about this IMEX AP scheme, which looks something like this. This is kind of a pseudocode for what I showed earlier, right? We, at each time step, sample something normally distributed, we do a positional update plus the normally distributed quantity, and then you have this random variable between 0 and 1, and we either have a collision or not a collision and resample. This is not actually how people in many cases simulate kinetic processes. So the sort of standard kinetic Monte Carlo would actually look something more like this. So the idea is you do a bunch of steps, but the steps don't have fixed length. You sample the next collision time from some exponential distribution. This more matches the physics of the real collision process underlying, so you don't have a discrete time step. And then you don't have to choose, do I have a collision or not? You just always have a collision after your tau. So this tau is sampled at each time step, changes. This is sort of the standard direct simulation Monte Carlo that you would imagine. And there is a variant to this scheme, which is here on the right-hand side, which basically is based on this. It introduces fixed time steps, so you still have this AP phenomenon in function of this discrete time step. I have the pseudocode up here, but the idea is basically the following. You sample this tau. If this tau is smaller than your time step, you simulate your kinetic process till time tau, then you pad the rest with a bit of diffusion, and then you do the same thing, and if tau is longer, then you simulate for the duration of tau, and then you pad to the end of the next time step. It's a slight variant. They look very similar. They've both been analyzed to some degree, and this one does get slightly faster convergence in Wasserstein distance on the ensemble, I think the fold analysis in L2 on the actual quantities you're estimating is still, I mean, there's a paper I'll cite later which has done some work in that direction. There's still a couple gaps there. But suffice to say, this is slightly better, at least mathematically. Not sure yet about actual computational cost. And we implemented this into a 2D fusion adjacent code, let's say, called iron. And I just wanted to show you that we have some more fancy looking plots in this setting. So here we have the kinetic regime, right? Where here we have our KDMC simulation. So this is the asymptotic-preserving scheme. It looks a bit peaked. There's this kind of exponential decay that I showed you before on 1D, but now it's 2D. We start the particles in the middle of this 2D domain, and we do a histogram at a certain point in time. I haven't plotted the reference solution, but just the difference, and you see that you have, 3 digits, 2 digits of accuracy in the computed solution, at the cost of about 10 billion particles, just to put that into perspective. So this is the high collisional case relative to the time step. We have convergence here, and this is what I mentioned. This convergence is actually even faster than the predicted rate. The predicted rate should be 1.5 in function of time step. We believe this is due to symmetry of the problem, so it's actually just a pathologically good case. And if you look in terms of runtime, the asymptotic-preserving scheme with KMC is much faster, we're the same. And basically, you save a lot of computational effort and get the same result. And similarly, in the diffusive regime, we have a similar thing. Now it looks a bit more like a bell curve, which you would somehow, you expect diffusion, normal distributions, Brownian motion. This is somehow also logical. And again, we have a similar degree of accuracy in our error plot. And we also get somehow a little bit slightly more wonky looking convergence plot, but as the collision rate increases, on the right hand side you get, again, convergence. And this is the main thing we wanted to observe. This is what I mentioned earlier. At some point you get these kind of upside down curves. You get convergence in both limits down to a noise level. But in this intermediate regime where you're transitioning, you get some kind of wonky phenomena. An interesting point here is that you see the kinetic simulation becomes more and more expensive as we increase the collision rate. I still don't know why that happens. But the KDMC stays relatively fixed. Yeah, this is just an extra slide to explain what this interference pattern is that you see in the middle, if you're interested, ask a question. With that, I think leave some time for questions. I would say, if you're interested in more details about what I talked about today, I would look at these 3 papers as a starting point. I mentioned in the beginning other topics we can talk about, so this is these reversible joints with reversible pseudo-random number generators, and Multilevel Monte Carlo, using Monte Carlo simulation to evaluate your likelihood, are interesting topics to me. These are somehow the main references that further that you might be interested in, so these are the AP schemes. This is another work on multi-level AP. And this is a paper I mentioned earlier about analysis of this kinetic diffusion Monte Carlo. With this being also other papers I cited at some point. So, thank you.